And we are from the Center for Applied Statistics and Economics at the Humboldt-University, Berlin. We start everything just assuming we have a complete market, we have an asset in this market, and the value of this asset at time point t is given by st, and we assume an existence of a risk-averse utility function that may be associated with a representative investor in this market, so we can write down the marginal rate of substitution between the asset price at time t and time capital T, and we call it the M. And this is also called the pricing kernel. We'll see later why. So we have a maturity here between today, t, and capital T in the future, maturity tau. And what we know that under risk aversion, U is a concave function, and it means that the marginal rate of substitution, or the pricing kernel, is decreasing. So M is decreasing on its argument. And what we'd like to do here, we have data, and we'd like to estimate M from the data. So we'd like to get M hat from data. And that's exactly what we do. We use German data from DAX index, and in this picture we see from DAX in 1999, May the 2nd, for a maturity tau of 10 days. Here you have the red line is the estimated marginal rate of substitution, or the estimated pricing kernel. In the horizontal axis we have the value of the index of our asset, and our asset is DAX index expressed in Manninen scale. And here the blue line we have the theoretical pricing kernel with a concave utility function. So we see here that the empirical pricing kernel is not decreasing across all values of strikes, across all values of the asset. So there are some regions on the asset value between 0.9 and 1 in Manninen scale in which the empirical pricing kernel is increasing. And this reflects some risk proclivity in the utility function from a representative agent. So we can see here that our empirical pricing kernel, or the estimated pricing kernel, does not reflect risk aversion across all values of strikes. And this is similar results were obtained by Aitzahali and Low and by Jacques Vert and Rubinstein using American data, so S&P 500 data. And of course, as we see here, the increasing pricing kernel implying risk proclivity. We'd like to see what happens if we change the maturity. Here in this picture we have again from DAX data, 2001, July the 10th. We estimate again the empirical pricing kernel across strikes and maturities, strikes in money and maturities in years. And we see here again the increasing region on increasing values of the strike. This risk proclivity region is also present if we go longer in maturities. And the question that we ask again is what happens if we change everything on time. So here again, the empirical pricing kernel estimated from DAX data in July, September, and November 2001. And you see again, the risk proclivity region between 0.9 and 1 is there for long maturities, for short maturities, and across time. So looking at these three pictures and the whole slides, we can verify from the estimated pricing kernel that the empirical pricing kernels do not reflect risk aversion across all strike levels. There are some strikes where the pricing kernels reflect risk proclivity. Moreover, the empirical pricing kernels, or the whole surface from pricing kernels, they change according to time t and time to maturity tau. So what we'd like to do here, and that's the question that arises, how can we explain the pricing kernel or the risk proclivity, risk aversion dynamics across time and maturities? So how can we explain, or how can we model the pricing kernel and risk aversion proclivity dynamics? That's the main idea of what we're doing. In section 2, we go very briefly to the description of, or definition of pricing kernel. In third, we will apply dynamic semi-parametric factor models that Professor Hedler talked about this morning for modeling the dynamics of pricing kernels. And the point 4, we show some empirical results. Well, in a general setup, we assume our asset price, the log of our asset price, follows some diffusion process where we have B is a standard Brownian motion under the measure P. This is our physical measure we call the objective measure. And we assume there exists a risk neutral measure Q, and the Hadron-Newtonian derivative from the risk measure P, Q respect to P at time t is given by zeta t. So we can write down the arbitrage fee price of a payoff psi from S. S is our asset with maturity tau as a discounted expected value on the risk neutral measure from the payoff. and we can write down this price change in the measure as expectation under the objective measure or the physical measure P from the payoff multiplied by a factor E minus R tau ZS divided by zeta t. That is exactly the definition of the pricing kernel M. Again, in a general setup, we assume we have a Merton optimization problem. We have a complete market with a representative investor, and this representative investor has a concave utility function. It means it's risk averse, and he has a stream of wealth and consumption, and at each time point S between today t and capital T future, he will adjust the amount CS invested on a risky stock in order to maximize the expected value under the objective measure from the utility of his final wealth, subject to the constraints that he will never go negative in his wealth, and his wealth will evolve according to gains in the bank account and gains on the risky asset. Everything is just to say that in a Merton equilibrium, we can write down the pricing kernel simultaneously as the marginal rate of substitution and as the ratio of the conditional density of the asset under the risk neutral measure and under the objective measure. So in this setup, these three objects are linked. The risk preferences from the investor, the state price density or the conditional density of the asset under the risk neutral measure, and the objective density. So that's exactly the strategy that Eitzahalian law use to obtain some information on the risk preferences from investor, doing some inference on the risk neutral and objective density. So again, Eitzahalian law in 2000 estimated the pricing kernel as the ratio between the estimated state price density and estimated objective density. And we know that the risk neutral density can be obtained from option data, so we have option data, and the P from underlying prices, the objective density. And the estimation goes, again, following Briede-Litzenberger approach and Eitzahalian law in 1998. The estimated state price density as the second derivative of the call price obtained with Black-Scholes formula, where the fifth argument is the implied volatility is smoothed on a surface, on a grid of strikes and maturities. The second derivative with respect to strike evaluated at S capital T. That's the estimator for the state price density. And that what we do here, we have data on option data, so we have option data, and we estimate the implied volatility surface using dynamic semi-parametric factor models. So we get a dynamic model for the implied volatility surface, and then we get the dynamics of the state price density. So we have option data, in our case on DAX. At each day t, we have JT trades on the option. So we have the trade J at day t. We observe option price, and this option price can be associated with the implied volatility at day t trade J, and this option is traded, and this option has a strike and a maturity kappa and tau, T and J. So we obtain this kind of data set that Professor Hedler showed this morning. So we obtain, for instance, at May the 2nd, 2000, we observed implied volatilities on a grid of strikes and maturities, and the data is observed following some strings because the maturities are predetermined by practical reasons. So we just observe certain maturities at a day, and we have this cloud of points across the whole year, and we know that with time, these strings here corresponding to certain maturity fall down as time goes. So the maturity comes close to zero. So all this data set across time and a year, they have some time dependency. That's why we use dynamic semi-parametric factor models to explain, to smooth implied volatility surface at every day here. And this implied volatility surface will be based on 3 or 4 time-invariant basis functions multiplied or loaded by a time series of coefficients. And these coefficients move on time. So these coefficients will explain the movement of the implied volatility. And that's exactly the dynamic semi-parametric factor model from this morning. Then we can, how to estimate. I guess in the talk from Shimon Borak tomorrow will be explained in more detail. So assuming we estimate the DSFM, so we can write down the implied volatility at time t, strike kappa, maturity tau, as e to the power of the product of the time invariant basis functions multiplied by the respective loading factors at time t. So in this sense, we will get the dynamics of the implied volatility surface described by this time series of loading coefficients. So we have capital L time series. And then we take this implied volatility and plug in into the SPD, the state price density, and we open the second derivative of the Black-Scholes call price. So we get an expression from the estimated state price density from our option data as a function of the implied volatility, but we see that the implied volatility will depend on the time invariant basis functions and the time series of loading coefficients. So we see here that the dynamics of the state price density will be controlled by the time series of loading coefficients. In implied volatility cases, it's clear what happens if one loading coefficient changes, what happens with implied volatility, but not in the state price density. So that's the approach. So we get the dynamics of the state price density through the time-dependent loading coefficients. And we go a step further and estimate again the state price, the empirical pricing kernel, using the Eitzer-Heilelu approach with a model for the objective density. So at the end, we will have the dynamics or the time behavior of the risk proclivity or of the risk of the pricing kernel controlled by time series of loading coefficients and time invariant basis functions. So the dynamics of the risk preferences will be expressed through z hat t. And what we would like to investigate is the dynamics of m hat. So if we're going to our empirical results, so we apply the model on DAX data. We have DAX index and options on DAX. We have ODAX for the year 2001. So from January the 1st, 2001 to January the 1st, 2002, have 253 trading days, and we use 4 time invariant basis functions, 0, 1, 2, 3. And that's based on Borak and I guess the talk from tomorrow. And we estimate the state price density using dynamics and parametric factor models, and the objective density with Garch 1.1 and a moving window of size 250 days, so almost 1 year. So what we get, here are the loading coefficients. The first is the blue, second is red, third is the green, across time from January to January. And these are the time invariant basis functions, the 0, 1, 2, 3. So at each time point t, we have 1st of July, we have 3 values of the loading coefficients. We multiply these functions with the loading coefficients and plug into the formulas, and we obtain the state price density, for instance here July the 10th, based on the loading coefficients. And do again the step further, we obtain the empirical pricing kernel across strike and maturities. Of course, we'd like to see how do the behavior of this time series influence the shape of the state price density or of the empirical pricing kernel. Then if you check here, this is the first loading factor. There's a big drop here, and we look down as September 2001. So we can see here is the end of August. The first loading factor has something like 0.6. And after September 11, the end of September, it has a value of 0.4. So we'd like to see what happens with the state price density and the pricing kernel in this time interval. And this picture shows, here you have the red line, here's implied volatility, state price density and pricing kernel. Here's strike, and we have a fixed maturity, so we have a slice of the surface, with fixed maturity of 20 days. The red line, maybe you cannot see, the red line is this one, shows the values of the implied volatility, state price density and pricing kernel in August 2001. The value of the first loading coefficient is 0.68. And the blue line shows the implied volatility, state price density and pricing kernel in the end of September 2001. The value of the first loading coefficient is 0.36. So we see a drop in the first loading coefficient shifts the implied volatility up. That's in accordance to results from our colleagues. So it controls the shift of the implied volatility. What we see the state price density before September 11th was peaked, and with increase of Z1, it flattens out. And that's something similar we have here in the pricing kernel. we have a risk proclivity region between 0.9 and 1, and as we increase the first factor, this risk proclivity region turns down to a risk aversion region. So looking at this picture of state presidency, what we see that it flattens out. So what I would like to do, or what we did, is to plot the excess kurtosis from the state presidency across time for a fixed maturity against the first loading factor. And that's what we did in this first plot. You have the red line here is the kurtosis of the state presidency across time. Here's January, here's December, and here's the first loading factor. So we see that they look pretty correlated, the series, and we see the correlation is 0.7. So something would tell me that the kurtosis of state presidency is controlled or is driven by the first loading factor. This is for a maturity of 18 days. We can repeat the plot for different maturities. So as we increase the maturities, we get longer. This is still correlation, but less correlation.
Doesn't it look like the skewness has changed a lot, as well as the kurtosis? When you have those pictures, can you go back?
Yeah, the skewness is also changed. Yeah, yeah. So here we have the third loading factor. We see here from January to April, the third loading factor increases a lot, and we see that skewness shifts the signs. So skewness shifts from one point to another. And this picture also maybe suggests there's some correlation between the skewness of the state presidency and the third loading factor. In fact, there's also correlation between the skewness and the second loading factor. And this is for long maturities. Then we put for shorter maturities. There are some variance in the correlation according to maturities. So this motivates to do some easy comparative statics. So we held everything constant, and we change one loading factor on a range of a minimal value to a maximal value. So everything else is held constant at median observed values. So then in this comparative statics, we'd like to see what's the effect of changing one loading factor when everything else is held constant, and observe what happens with the skewness and kurtosis. And therefore, we have to define some new synthetic weights or artificial weights. This exactly everything is held at the median, and the selected loading factor is increased linearly according to some number of steps. And that's what we have here. In the left panel, we have change in the first loading factor. Here we have implied volatility shifts, and we have a change in the kurtosis here, also in the skewness, but mainly in the kurtosis. The third loading factor has some skewness change in the implied volatility for a fixed maturity. There's also some skewness in the term structure from the implied volatility, and we have some change in the skewness from the state price density for this maturity, and this change in skewness is also different for term structure. So basically the third loading factor controls skewness and term structure from the state price density. This is show what happens here. We increase the first loading factor from the artificial loading factor, and here's the kurtosis from the artificial state price density across maturity, so it increases across all maturities. And then is just a plot from the also artificial pricing kernel. We have here for a fixed maturity, here we have strikes, and here we have the values of the first loading factor. So we see for very small values of the first loading factor, there's practically no risk proclivity. And as we increase the first loading factor, we see risk proclivity at the end. And we can do the similar exercise with the skewness and the third loading factor and the skewness and the second loading factor. Well, the main findings of this idea is that the pricing kernels and risk preference dynamics are driven by the loading coefficients from the SFM model. The first coefficient controls level of the implied volatility, excess kurtosis of state price density, and very loosely and informally speaking, the existence of risk proclivity in the pricing kernel. The second loading factor controls the skewness on the strike direction from the volatility, from the state price density, and again, very informally speaking, the location of the risk proclivity. And the third loading factor, again, the skewness, but there's some term structure. So it means that the skewness will move differently for different maturities. That's what I had to say. Thanks for listening.
Any questions?
Kernels about and gave one way to estimate them, at least theoretically. So I just focus on the hypothesis that can explain price in kernels, and so exactly what we observe in the markets. So, we have, as Enzo said, we have data coming from two markets, from DEX markets and from the options on the DEX. And basing on these two data streams, so we can estimate, wait a second. We can estimate the price in kernel as density of two, as a ratio of two densities, the risk-neutral density Q and the subjective density P. So Q can be considered as price of contingent claims on ST, its continuous version, and P is the distribution of those, which gives some idea about the probability of the states. So basically, this is nothing. It has, this price in kernel has another name. It's called price per chance, and this name actually elucidates its meaning. So it's Q is price, P is the probability in some continuous version. So we can estimate the density P from the DEX data in our case. So in this work, there were several models tried, like gauge, discrete Heston, or non-parametric kernels. And for example, one model that was to which particular attention was paid was the Heston model, which is the stochastic volatility model. It is driven by two Wiener processes, W1 and W2. So the first process, the second process drives the volatility. For this process, we can get the closed form solution, and we have the characteristic function thanks to this work of Carr and Madan. And then it is calibrated, its parameters are calibrated to the data. The subjective density P I was estimated in several using several models, for example, the Gaussian model or kernel models. And so it's here exactly how these two densities look like, what these two densities look like. So the first is the historical density, and the other is the risk-neutral density for one date. But these pictures are very similar, or so they have some small features differ, but usually the first has two peaks, the other has one peak, and they have different skewnesses.
Which one is the historical?
Historical is the first one. This has two humps. That's P, and that is Q. So the density Q has only one maximum due to the process that's assumed. So it can produce only one maximum. So if we divide these two, we get the empirical pricing kernel, which looks like which is generally decreasing, but around unit returns it has the hump, so it's not monotonous. So if we look, okay, and this picture actually is quite persistent over different times and over different methods. This means that the relative risk aversion coefficient, if you estimate in the classical way, is negative, which implies risk proclivity. Very interesting that the risk proclivity appears in the region of unit returns, so approximately unit returns, where most of observations, or like at least mean of the distribution, is located. So we have many observations. So what we can expect from the theory? So the theory, like CAPM model, may tell us that the utility function is quadratic, then the pricing kernel, which is essentially the first derivative of that, or marginal utility, is linear. We have another theory, another model that uses the CRA function of constant relative risk aversion functions. But in practice, this doesn't change the situation a lot, and it leads, because constant relative risk aversion function is very smooth, and it leads actually to well-known equity premium puzzle. This didn't appear in the original paper of Kahneman and Tversky, but was just artist's kind of impression of what they try to convey. This is based on some behavioral experiments, and the important feature of those is the reference point exactly around this break. So behavior of the investors above and below this reference point differ. So the marginal utility is higher on the left-hand side from the reference point, because investors care more about losing money than winning money. So also there was another work which will be presented tomorrow about price and kernel monotonicity test by Roman Timofeyev. So it seems that price and kernel is not monotonous. Exactly, it has this hump, which contradicts primitive economic considerations that say that states of the world that are good, that correspond to higher returns, in these states of the world, contingent claims that pay €1 should cost less than in bad states of the world when returns are low. So this is not that simple.
What about, say, the options are put options, in which case up is bad?
It could be one of the reasons. Yeah, actually, it was one consideration that it could be like that. Here we used call options actually, so
Just took call.
it was only call options we used. But actually, exactly this was a result in Breeden-Litzenberger that basically the density is the second derivative of the call option, and call and put option are related. So probably there shouldn't be any. So if we don't want to violate risk neutrality, we could use also put options somehow. It just will be different sign-off. So the idea is the following. So if we look at the utility functions again, pricing kernel is virtually a marginal utility function, and if we integrate the pricing kernel, so we get the function that is represented with this red line, if you can see it. So it's not concave as the theory prescribes, or simple theory prescribes, but amazingly this function can be quite well approximated with two segments. So the lowest segment, approximately below returns equal to 1, is very well approximated with the CRA function, and the region above unit returns is also reasonably well approximated with another CRA function. Then we can, but if we so then we can think that there is some kind of switching going on. It's just, again, hypothesis that there could be some switching going on between these two regimes. And here I represent one of those mechanisms of switching when the lowest segment remains constant and the upper segment, which is this green line or a pink line, it just moves backwards, shifts backwards and forwards. But you may say that, okay, if one investor switches at some particular point For example, so you move along this blue curve until you cross the first pink line and then curve, and then you move upwards. So that would be investor one that switches, right, between these two types of moods or behavior, if you want. So how can you obtain this smooth utility function that you observe in the market? So the answer could be that when investors are, the many investors with different switching points in the market, like here you can see, imagine that there are three investors, two have pink lines, and another is corresponds to the green one. So they interact with one another, and you do not, I mean, as a result of those interactions, you basically don't see the sharp change. So this discontinuity is just smoothed out. And exactly so, there were some simulations performed, and I just will show one result, aggregation result. So indeed it happens that when we have many investors which have which has utility functions with singularities like that, the singularity like single out these non-continuities. So we can think about these investors like two investors which correspond to this left line and to right line as, for example, optimistic and pessimistic investors. For example, this investor keeps to the blue curve, to the blue kind of part of the utility, his utility, which we call the bearish, which correspond to bearish attitudes, until he reached this point when the blue line crosses the first pink line. And at this point, this investor thinks that now market has changed the regime, and now market is bullish. And this kind of euphoria that in the market gives this investor additional utility, boosts his utility, so he switches to the pink line. Another investor, the second investor, switched much later, and this investor is rather pessimistic. So this investor really requires high returns, which are well above 1, to perceptually believe that market is bullish now. And the aggregation interaction of these investors really leads to something that we observe as the representative investor utility function, which is red here. Again, there can be different mechanisms for aggregation. The simplest is just to sum up utilities, which is the worst, of course. We propose another aggregation, which is based on perceived states of the world. If you think of some economic situation, is basically when people sit at the table and they decide, so when they're equally happy, for example, they decide what returns should be allocated to each investor to make everybody so happy. I mean, so in this case, the state of the world is given with the level of utility. So it's another way of aggregate, or you can aggregate in the classical way. It's just maximizing utility subject to some constraints, budget constraints. So that's another way. This way of aggregating gives, of course, unique solution, obviously. If you do aggregation using classical ways, it's like trading going on based on some auction type, then of course you can expect multiple equilibria because the utility function is not concave. And in which equilibrium you end up depends on what kind of auction you have. Interesting thing here might be to study might be that so you can get actually probabilities of ending up in different equilibria, which depend on the type of the real auction. So sometimes you end up in one equilibrium, sometimes in the other. And so it's kind of, so the system displays some kind of chaotic behavior actually, because there's so many switching going inside that you easily kind of find out in one or other situation or state. Okay, this. So, and this is one of the problem that is. So sorry, I just. This is one of aggregation mechanisms. Again, it's quite non-classical, which is well understood. So we have some utility level U, and it's not trading. It's some kind of social plan or whatever problem. So we have some utility U, and then we look at returns that each investor would demand. So we have n investors to end up with this utility U. And then we define actual states of the world in terms of utilities. And returns, so basically in this case we're not aggregating utilities, we're aggregating returns. That's why this problem is invariant to any transformation or monotonic transformation of utilities. So the result will be the same. So it's a good feature. And returns will be just that integral. So it's inverse utility function, which is integrated with the density of x. And Fz. Fz is the density of switching points. So Z is some characteristic, the switching point is the characteristic of each investor. This problem can be solved. This problem is convex. It has, we can use standard quadratic optimization tools for solving this problem and get the distribution. We have several dates here. So this is estimated for March 2000. So basically, this is the date prior or just during this dot-com bust. So half year, we're looking at half year returns. So this is supposed to be bullish market. You can one feature is that comparing to this picture that investors the distribution is switched to the right from the unit returns. This is the stable market, and this is the bullish market. Sorry, this is the bearish market. This is stable market. For the stable market, which is worse than the bullish market, investors are more critical. So the distribution is shifted to the left, which means that distribution is shifted to the left, which means that investors actually switch to the optimistic mood or the bullish mood earlier. Okay. Right, and yeah, and this is the for the bullish market. So when you're in the bullish market, investors require higher returns. So basically the distribution is shifted to the right here compared to the stable market, which means that in order to perceive the situation, the bullish market as additionally good, so investors would demand even higher returns because you may think that they got used to already higher returns that govern in the market. So this is it, and yeah. Again, additional, so this research hasn't finished at this moment, and the next phase would be to introduce different aggregation procedures and different auction types to study the nonlinearity of the solution, because again, it's not the convex problem. So, and this problem has many internal switching points. That's why it's actually can be treated as stochastic, or chaotic system, which solution cannot be very well predicted, but can be described as the distribution. Okay, and thank you. And if you have questions, welcome.
Why did you try to use some non-expect utility to see if it fits the results what you observed about the two peaks in the...
So what kind of utilities?
Like some non-expect utility, like you mentioned about the prospect theory, but that's still about you try to use one utility index to explain things, but they discount the loose. But I would suspect if you use true the chaos betweenness utility.
You mean like switching, like a Markov chain and switching between?
They impose a higher weight on the tails than the
Yeah.
objective.
It could be one explanation because if you think about utilities, you can think about probabilities of this. I mean, it consists of two components: probabilities of the states and the value function itself. And so the value function can be all right. It could, but people just may understand probabilities differently. Maybe this is the answer.
In the